All right. Welcome everybody to the Georgia Tech Graph Theory seminar. And our speaker today is Yifan Jing from University of Illinois at Urbana-Champaign, who will tell us about generalized sum product phenomena and the related coloring problem.
Okay. Thank you for having me. Today I'm going to talk about this, generalized sum product phenomena and the related coloring problem. So I will start with the notation sumset and productset. So when G is a group and this multiplication is a binary operator in the group, we define the product set A times B to be this little a times little b, where A is an element in A and B is an element in B. And when the group is abelian, so the operator is the addition, then we just denote A plus B by the sum set, so A plus B. And in general, let K be a field and P is a bivariate polynomial in this field K. We can write P of AB to be this P of little a, little b, where A is in this capital A and B is an element in capital B. Okay. And so I begin with a general, very interesting phenomenon in combinatorics. So basically, if you have some reasonable notation of size, say if the set is finite, let's say cardinality or higher measure when the set is compact measurable or Banach density or even like upper density, etc. So you have this some reasonable notion, and then we expect the size of AB will be much larger than the set of A and set of B when we chose AB randomly. So AB is a random set, then and also the sequence A squared, A cubed should grow rapidly. And here are some examples. So for example, in this integer setting, if A is chosen randomly, then we expect A plus A have size n choose 2, because like we choose for A randomly, so we have low probability that A plus B equals C plus D for 4 elements in A. And then if similarly, we have A plus A should be n choose 3. And also in a free group for this non-abelian setting, and then if A is a generating set, A and B, then A to the power of n is just 2 to the power of n, because all the different words represent different elements in this group. And also in SO3, three-dimensional rotation group, we can because it is a compact Lie group, so we have this normal. We can define a normalized higher measure on this group, and then we can choose rotations along x-axis, y-axis, and z-axis, and each of them are maximal torus, have lower dimensions, so it has measure 0, and the product of them have its entire group. So so you can see that small like px, ty, tz, all of them have measure 0, but product of them could have measure 1, the total measure of group. So that tells us in general we will have a really large expansion if you have like A and B if they don't have some special structure. So that means, on the other hand, if A and B have some additional structure, then we expect sets A squared over set of A, we call it doubling constant, become much smaller. And then we can have, there are also a couple of examples. For example, if A equal to a arithmetic progression of first 10 integers or 11 integers, if 0 is also an integer. So then A plus A is just from 0 to 20. You can see that A plus A is pretty small in this case. And also in continuous setting like T squared to be a two-dimensional torus, and then we can take A as a strip in the torus. So let me maybe I can draw something. So this is T squared, and then we can take A to be a strip, something like that. Okay. And then you can see that in this case, if you consider A squared, then basically the width of the strip get doubled. So the measure only get doubled, only have factor 2, expansion factor 2. So it has small expansion. And also when G is very non-abelian, for example, in this case, you have this SO3 times a torus, or any like non-abelian, very complicated group times a torus. Then if A is essentially controlled by a nice set in this torus, then A squared also have a small expansion, right? So okay, maybe I can also draw something here. So in general, like this group could be a like weird manifold, but then the base is like let's see a torus. So okay, let's see, can I draw it nice? So the group is like this. Okay, it looks like a bread, but you can see that. And then we can choose a slice of this bread, like this. And then this set is essentially controlled by this torus. So the expansion is small. Okay, so let me clear out my drawing. Okay, so actually there are converse theorem also tells us some similar phenomenon. So for example, Feynman theorem tells us if a plus a is smaller than 3n minus 4, so a is a subset of integer of size n, then a contained in a arithmetic progression of size at most 2a, 2 of size 2n. And in general, if a plus a is smaller than ka, then a is contained in a generalized arithmetic progression of bounded dimension and bounded size. So that tells you if a is a subset of abelian groups, then a have some additive structure. And this is later generalized by Green and Rusha in 2007. So if a plus a is smaller than k times a, then a is contained in a small coset progression. So because in a general abelian group, we have coset. So coset progression is just a coset plus a generalized arithmetic progression. And the small means arithmetic progression have bounded dimension and bounded size, basically. And we also have a same phenomenon for non-abelian group. So for example, in a celebrated result by Breda, Gray, and Tao, in their proof of the structure of all approximate groups. So if S is a finite subset of some general non-abelian group G, and S cube is small, have small tripling, then S can be covered by a small number of small coset new progression. So new progression basically a pullback of coset progression in nilpotent group. And we can view that nilpotent group as a suitable generalization of abelian group. So basically in this case, S is also controlled by some abelian structure. And not only S, but also G is also controlled by this some abelian structure in some sense. And here, this is a recent result by me and Tran. I think he is also here. So we prove that in a locally compact group G, and A is a compact subset of G with small expansion. So mu A square is very close to 2 plus C times mu A. Okay, the G should also be connected, because if G is not connected, we can just choose a small a subgroup of G. And in this case, A is close to a Bohr interval. That means there is a continuous group homomorphism mapping from G to one-dimensional torus. So that means G is essentially controlled by this one-dimensional torus, just like what I drew before, that bread, right? So this group is essentially controlled by a one-dimensional torus. And then A is a pullback of an interval in this one-dimensional torus. So basically, A is a slice of the group.
Okay. What is C here?
C is a very small number, like 0.01.
Mm-hmm.
I don't have enough space to write down, but C is a very small number.
Mm-hmm.
Okay, and all of those examples tells us some interesting phenomenon that a finite subset of expansion behavior under some binary operator. So basically, A plus A or A times A should be large, unless the situation is controlled by a single abelian group. So you can see that single abelian group means, so if you have abelian setting, A should have some internal additive structure like an arithmetic progression. And in a non-abelian setting, A should be controlled by some abelian group. So one can think like actually non-abelian group give us in some sense a field structure. So one can see that, for example, all the linear group, so the subgroup of GLN. So this matrix group, actually you have addition and multiplication in this matrix group. And then in some sense, it can be seen as a field structure in some sense. And then the set A is essentially controlled by one abelian group. And this interesting phenomenon also, of course, hold for field. So this is known as sum product phenomenon. So this theorem is proved by Erdős and Summerady in 1983. There exists a constant C greater than 0 such that all set of integer A of size n. So the maximum among the sum set and product set will be at least n to the 1 plus C. Okay. Yes. So basically, yes. So basically, you can see that if you ignore this 1 plus C, so we can see that if A plus A is smaller than K times n, then A should look like a arithmetic progression. A times A is smaller than K times n, then A should look like a geometric progression. So you know that a written progression is not a geometric progression. They look very different. So in that case, we can see that the maximum among a plus a and a times a should be larger than n to the power of 1 plus little of 1. So it cannot be like k times a. But in order to have this constant c is pretty non-trivial, actually, this result. And actually, there are lots of quantitative improvements on this, about this c. So in 97, Nathanson proved we can choose c to be 1 over 31. And then it improved by Kevin Ford, we can take 1 over 15 in 98. And later, so there are a lot of improvements start by Elekes. He used this summated charter theorem to prove some product estimates. So he proved we can take C to be 1 quarter, 1 over 4. And then later improved by Scholemachi 3 over 11. And then in a very famous paper by Scholemachi in 2009, he finds some like geometric property of these lines can improve this result to 1 plus 1/3. And also there are lots of later improvements based on Scholemachi's argument. So you have this 1/3 plus 1 over 1500. And then by George Shaken, he's also a graduate student at UIUC. So this is a quite famous result. I think like Quantum Magazine also have a report on that. So you can improve this by 1/3 plus around 1 over 1000. And the current record is by Ratnov and Stevens recently this year, I think in April or May this year. So they improved this result to 1/3 plus around 1 over 500. But today we are not going to talk about these quantitative improvements. It will be a very different story. So there's a very famous conjecture, which is largely believed to be true, but pretty hopeless. So we can take C to be 1 minus epsilon. So basically a plus a and a times a, the maximum should be almost n square, like n square minus epsilon for every epsilon. Okay, so this is one interesting phenomenon for field. So this is so a is subset of integers in this case. And then there's another very famous result by Elekes-Ronyai in 2000. So they also prove a similar phenomenon for general two bivariate polynomial. So we can choose k to be either r or c, and then we choose p to be a polynomial with two variables with non-trivial dependence on both variables. That means it's not like one variable polynomial. We should have two variables. Then either you can find PAB is large, or PAB have some structure. It's either additive form or multiplicative form. So additive means P is essentially a sum of two one-variable polynomials. A multiplicative form is P is essentially a product of two variable polynomials. So this is also a very interesting phenomenon on all of these small expansion sets. Basically, this polynomial should essentially controlled by a single abelian group. So you have a field, so you have two binary operator plus or addition or multiplication. But in order to have small expansion, you have to choose your favorite binary operator. So either plus or multiplication. Okay, and the value of C can be taken arbitrarily close to 1/3 by Russ, Sherry, and Scholemachi in 2016. This is the quantitative improvements. And so there's an interesting question asked by Zeeuw. So what can be said when A equal to B? So if we know that PAA is small, can we have a better structure of the polynomial? This is an interesting question. And also people consider a similar phenomenon for pairs of polynomial. So if you have two polynomials, P and Q, what can be said when PAB and QAB is small? So the maximum among the image of PAB and QAB is small. So any guess? So if PAB and QAB are small, what can be said about P and Q? So from Elekes-Ronyai theorem, we can see that if one of them is small, it should be either additive form or multiplicative form. And we said before, like a structure has small expansion, then it should be controlled by a single abelian group, just like in Feynman theorem. if A plus B are small, then A and B should be controlled by a same arithmetic progression with same common difference, right? In that, like, if A plus B is smaller than like 3q minus 4 theorem in that one. So we may guess in this case, A and B should be either additive simultaneously or both multiplicative form. So this is our guess. And actually, this problem is well studied before. So you can see that Erdős and Sumret studied x plus y and x times y in their sample like estimates. And later, Elekes, Nathanson, and Lucia studied the case when P is x plus y and Q is fx plus fy. So Q is essentially a sum of two one-variable polynomials. And Shen in 2012 studied the form like P is x plus y and Q is an arbitrary bivariate polynomial. Okay. So yeah, so our main result here, the first main result, basically answer the question when you have arbitrary two different polynomials. So here P and Q are arbitrary two bivariate polynomial in K, and then K is either R or C. So you have three cases. So exactly one of the following holds. So either you have large expansion for every A and B of size n and large enough n. So PAB and QAB are large. And then, or like PAB both have additive form, or P and Q both of them have multiplicative form. And also these additive and multiplicative form, they share the same one variable polynomial. Okay. And this is joint work with my friend Roy. He's also a PhD student at UIUC, and also Min Tran. He's currently a postdoc in Netherlands. And by taking P equal to Q and some other argument of polynomials, we can prove that this actually answers a question asked by Zeeuw. So if you have A equal to B, then we have a better structure characterization. So P should behave like UX plus UY. So both of them should have look like a same variable polynomial. And in this multiplicative form, it should also like UX to the power of something times UY to the power of something. They should share the same one variable polynomial. Okay. So yeah, I want to point out that this bound here is not sharp. So we didn't really try to optimize this bound here. Okay. So any questions until now about the statement of the theorem?
So in addition to saying that the polynomials, if the sum in this PAA or PAB may be small, in addition to just saying something about the polynomials themselves, can you also say something about the structure of the subsets A and B for which this maximum is small, in terms of maybe these univariate polynomials inside of P and Q?
I see. So
like you would say for just, say some sets, that if the sum set is small, is because the set A is close to union.
Yeah, I see. Actually, that's a very
progressions.
interesting question. So you're asking, like, if we fix P and Q, say we already know that this is non-expanding polynomial, for which A and B you actually get this non-expanding property.
Yeah.
Yeah, that's a very interesting question. We know that when P is like x plus y, then it's just Feynman theorem, and x times y also Feynman theorem. And for general P and Q, yeah, I have never think about this question, but yeah, it's a very interesting problem to explore. Okay.
I think that is really hard question.
Yeah. For general P and Q, it should be hard.
Yeah. But even for addition and multiplication, that's very hard.
Yeah, for addition and multiplication, we only have characterization when we say like A plus B smaller than K times n. So 2A plus smaller than K times.
Right, I see.
But if 2A smaller than n to the power of 1 plus epsilon, then I think it is unknown in general. The structure is pretty hard.
I see.
Okay. And also here, I assume K is either R or C. By a standard model theoretic transfer, we can transfer the problem to all the algebraically closed field of character 0. So as I mentioned in the next page, so we can transfer the results to all the algebraically closed field and real closed field of character 0. And using some basic Galois theory, and then we can also transfer the theorem to all the field with character 0. So we can remove this algebraically closed condition. But in order to remove this algebraically closed condition, we have to replace exactly by at least. You can see that in the proof. In the theorem, we said exactly one of the following holds. But now if we replace K by just arbitrary field of characteristic 0, we have to replace this exactly by at least. So here's an example constructed by Zhang. So you can see that x squared plus y squared. This is not an expanding polynomial in C, but it is an expanding polynomial over Q. So Q is a field of character 0. So you may have, yeah, okay. So I want to give you some proof. So firstly, I want to present this Elekes proof of some product estimate. Maybe most of you have already seen this before, but I still want to present it here because I like this proof, and this is one of my favorite proofs. Okay, so before I will just tell you the summarized structure theorem. I think maybe most of you have heard about this. So if G is a bivariate graph with vertex partition P and L, so P is a collection of points and L is a collection of lines in R square. And then we assume P have size M and L have size N. And for every point in P and every lines in L, if V1, V2 is an edge in this graph, only if we have these points lies in this line. Okay, so this is actually the instance graph, actually, you can see that. And summarized structure theorem tells us the number of edges in this graph is at most mn to the power of 2/3 plus m plus n. Yeah, so this is a very nice theorem. Can be seen as the Rankin-Rich problem because the graph is also K2 to free. Okay, so Elekes firstly find that actually we can use summarized structure theorem to get a really nice proof of Elekes of the sum product estimate, the Erdős summarized theorem. So the proof goes as follows. It's actually pretty short. So we consider P as a collection of points, contain all the points in this. I want to hide this. Contain all the points A plus A times A. So you can see this is a subset of R square. And then L be the collection of points. L A B where we can define this, collection of lines. Y equal to A times X minus B, where A, B are elements in A. So why we define some points like this, some lines like this, you can see that if we X taken values from A plus A, so X had form C plus, like X plus B, X is an element in A and B is an element in A. Then X plus B minus B, we plug in X here, then Y would lie in A times A. Okay, so this is why we choose such lines. So that means, so the number of lines we have is n squared because we can choose, say A have size n, so we can change n different number of A here and different number of B here. So L have size n squared. And for every line in L, it passes through at least n points in P because we can choose points of the form B plus another element in A. And then for the value of X, like B plus C, and then Y would be A times C. So it's also lie in this product set. And now by the summarized structure theorem, we know that now the number of instances we have is we have n squared lines and each line pass through n different points. And also we can see that for two different lines, it represents, different lines. They cannot be the same line because the slope are different for different A. So we have n squared distinct lines and each line goes through n different points. So the instance is n cube. And then by summarized structure theorem, the instance is at most the number of points to the power of 2/3 times the number of lines to the power of 2/3. Okay, and this implies this A plus A times A would be at least n to the power of 5 halves. So that implies the maximum among A plus A and A times A should be at least n to the 5/4, 5/4. Yeah. So it's a really interesting and nice and short proof. Okay. So yeah. So basically, in our proof, we also apply the same fashion of this Elekes argument on this using the Sumset-Chatter theorem. But here we need a more general Sumset-Chatter theorem, the Sumset-Chatter theorem for semi-algebraic bipedal graph. So a bipedal graph is semi-algebraic if the vertex set is defined on the can be embedded in the point in R to the power of D, D-dimensional Euclidean space, and edges are given by a set of polynomial equations and inequalities. So we can view that. Okay, let us assume this G have vertex partition V1, V2, and all the vertices are points in R to the D. And for one point in V1, another point in V2, so this there is an edge between V1 and V2 if and only if these 2 points satisfy this a branch of polynomial equations and polynomial inequalities. And we further require the graph have bounded complexity, that is the number of inequality and equations is bounded, and also the degree is bounded for polynomial equations, inequalities. And this is a very, very nice result proved by Fox, Pak, Sheffer, Sok, and Zeeuw in 2017. Actually, their result is for a more general semi-algebraic bipedal graph, not only in R square, but also in D-dimensional Euclidean space, by replacing these 2/3 by D over D plus 1 plus epsilon. So when dimension D is larger than 2, there's an epsilon loss here. So the reason is in the proofs they apply this Kowalski's, Shen, and Tran theorem. So they use a cell decomposition of graph, and then in each cell they apply this trivial upper bound on this KDD free graph, and then actually K22 free graph, and then they just combine this cell together. But in this combination, so they have this epsilon loss, so in general. But for D equal to 2, there's no loss. We have this sharp bound. And we only use the case when D equal to 2-dimensional case. So if G is a semi-algebraic bipedal graph with bounded complexity at most T, and then so if the graph is KDD free, then we have the number of edges is at most this number, mn to the 2/3 plus m plus n. And this constant coefficient only depends on T and D. Oh, so there's no D. There is D. So here I use KDD free. Depends on T and D. Okay. So in the actual proof, we just apply this. The first step of our proof, we just apply this Sumset-Chatter theorem in the same fashion as what Elekes did in his proof. So assuming we are able to apply, you can see that here we have this extra condition KDD free, but assuming our graph is KDD free. So let's do this. We assume A equal to B. So we can, for the simplicity, so we can consider the same construction of curves. So in Elekes proof, we construct a bunch of lines. So here we can construct a lot of curves. So this curve taken points PAT and QA prime T for some fixed T in R. For T in R and fixed A and A prime. So this is indeed a curve. And this curve is semi-algebraic because we need to take inverse of polynomial. So it's not algebraic, it is semi-algebraic. We have these polynomial inequalities. And then, so the instance relation gives us a semi-algebraic bipedal graph. Okay, so we can consider points and curves. So both of them lie in R square, 2-dimensional Euclidean space. Assuming we are able to apply Sumset-Chatter theorem for semi-algebraic graphs, then we can prove by applying the same proof as what Elekes did. The maximum among P and Q should be at least n to the power of 5/4. So we have large expansion. So in other words, if the graph is KDD free, then the 2 polynomials should be expanding. We have expansion. So the main difficulty, the main contribution of our paper is to deal with when the graph have large KDD. So now we can assume our graph is not KDD free for any constant D. Okay, let me see. So I will just give you a sketch of the proof without going into details. So first step, we use this algebraic boundedness. It can be seen as an abstract Zeeuw theorem. So the graph is semi-algebraic. So we can view that we can define a reasonable dimension because basically definable sets in R are essentially real manifold and definable sets in C are essentially algebraic varieties. So there is a good notion of dimension. And then by this algebraic boundedness, so basically, so this phenomenon is basically the intersection is bounded by constant, or it have dimension 1 intersection. So using this result, we can, okay, so in the previous slides, we defined curve to be to taken values in A and A prime. But if the graph is not KDD free, we can just construct dimension 1 number of curves, taking values for all elements in R. So let's consider R case. For every A and A prime in R, we can define a curve. And then this curve, we can prove that this curve contain a large, like KDD, and both D have dimension 1. So basically, that means you have infinite or dimension 1 number of curves, and all of the intersection have dimension 1 intersection. That is like interval, something like interval intersection. And then we also use a definable Erdo-Channel property. That is, we can find, so here we have a large KDD, and then we can find a curve, a fixed 1 curve, dimension 1 interval of a curve, and then we can prove that there are infinitely many curves contain the same these intervals in some sense, and these infinite many have dimension 1. So basically, we can, let me draw something. So we can find a curve like a dimension 1 part, like just like an interval, such that there are infinite many curves go through the same interval, contain the same interval, something like that. And also the number of curves have dimension 1. Okay. And then we just use abstract cell decomposition. We can decompose X, because X is a kind of interval of a curve. We can decompose X into several locally analytic curves. And then we can apply the Elekes-Ronyai theorem in such polynomial. We have, so we have P and Q are either additive or multiplicative. Now we want to prove that they cannot be, one of them is additive, the other is multiplicative. And this cannot hold because we can just, the curve is analytic, so we can just take derivative and then to show that this curve should have the same form. So this is the argument, like the sketch of the argument. The actual proof is more complicated.
May I ask a quick question?
Sure.
So why are these curves not algebraic, but semi-algebraic?
So this curve is defined by this.
Right. But parameterized curves like this, aren't they algebraic?
Okay, let me think.
Yeah, because it's like xy is a point on this curve if and only if some resultant is 0 or non-zero. Yeah, 0.
Okay, so I haven't think about this too much because we can just apply this. I just view this semi-algebraic semi-algebraic structure as a black box, so it should also apply for algebraic curve. But I think
the reason I'm asking is that because from the sketch on your next slide, when you said that you have these curves that overlap in the dimension 1 bit. I mean, if they're algebraic, the only way for them to, I mean, it's much more constrained somehow, right? How they can overlap. They have to essentially share an irreducible component then, if they.
Yeah, I see. Let me think.
Shall I say something?
Yeah, sure. Okay.
Yeah,
if
so
you still
these
remember
are
the proof.
image of algebraic thing, right? So if you are looking at the set PAT, QAT, right, that could be algebraic. But here you are letting T range over R, so it is image of an algebraic set. Right? So that's why it's semi-algebraic.
But if the dimension of intersection is 1 over R, can it? I mean, you can consider this as embedded into complex number, right? And then if the intersection was dimension 1 over R, it would still be dimension at least 1 over C, right?
Right. So if you are looking at in C, then it's algebraic, right? Because just because of
in C it's algebraic. Yeah, in C it's algebraic.
But here in R, you won't have it algebraic.
Yeah. Yes.
Yeah.
Okay, I kind of remember the proof. Okay. Okay, so yeah, we can discuss a little bit later because I have
Yeah.
Sorry. Yeah, I remember in C it's algebraic, but in R it's different. Yeah, so we proved this result a year ago, so I'm a little bit forgot about details, but yeah, we can discuss it later after the talk. Okay. Yeah, so this is KDD free case. And then and then I want to show a nice application. Actually, I didn't really apply this result, but use this phenomenon, we can kind of solve another problem in another coloring problem in graph theory. So recently, so there is okay, let me tell the definition first. So we say two copies of H are color isomorphic. So we color a complete graph Kn H coloring. And then we say two graphs are color isomorphic if they just have the same color. And you can find a bijection of the vertices, and then all the edges have the same color. So here's the example. You can see that 2C4 are color isomorphic. And then we can study this as a generalized version of Tran number. So for any fixed graph H, we define fk of an H to be the smallest integer C, such that there exists a proper H coloring of Kn with C colors containing no K vertices joined H are pairwise color isomorphic. So we can find the minimum number of coloring such that we don't have too many color isomorphic copy of H. And then in this talk, we just focusing on C4, the cycle of length 4. And it is proved by Colin and Tomkin. I'm sorry if I pronounced his name wrong. So they prove that there exists an integer k such that fk of nc4 is linear. So you can see that when k is getting larger, this number is getting smaller, because if you can find if you don't have k disjoint color isomorphic of H, then you cannot have k plus 1 color isomorphic copy of H. So basically, actually the result is for all cycles, for all even cycles, you have this. And in their proofs, they use random algebraic argument. So the number of k they get is pretty large. It's like larger than 10,000, something like that. And then the question is, can we find the smallest k such that fk nc4 is linear? And in particular, Colin and Tomkin ask, can we take k equal to 2? So basically, can we use linear number of colors to color to H color Kn such that we don't have any color isomorphic C4? So this is the question. Okay. And we didn't answer the question asked by Colin, but we find another very small number k. So actually, we proved F3 and C4 is linear. So you can use linear number of colors, and then there's no, you can find at most 2 color isomorphic C4. So this is our result. And this is joint work with my lots of Chinese friends, Genyan Ge, Zixiang Xu, and Tao Zhang. This proof very recently. So because if you use random algebraic construction, then this k will likely to be very large. So here we use a deterministic algebraic construction. So we choose a field k, and then we find an embedding of vertices in k. So all the vertices are elements in this field. And then we choose a symmetric polynomial p, two-variable polynomial pxy. For every ab, 2 vertices in V, we color the edge ab by p pi a pi b. So basically, we just color the edges by these the image of the polynomials. And then we hope that under this coloring, we want to choose a nice polynomial such that under this coloring, we have proper edge coloring, where like each color class have bounded degree, and by like if we have this, then we can easily modify it to a proper edge coloring. And then also we hope that we don't get too many color isomorphic C4s. So this is a hope. Okay. Yes. So the key difficulty here is to choose a polynomial. how to choose a polynomial? So first we can assume our K is a field of characteristic 0. Let's say we have something like that. And P is a bivariate polynomial, it is symmetric. And then pi is an embedding of vertices in K. So all the vertices are elements in this field. And also, okay, because we want to show that like Fk and C4 is linear, so we want the total number of colors is linear. So we want the image of P pi v is linear. And then this polynomial have small expansion. Then by our results, we know that the structure of polynomial is either ux plus uy or, sorry, there should be another f, or f of ux times uy is either additive form or multiplicative form. And because the polynomial is symmetric, so we can remove this like different exponent. Like in the original theorem is ux to the power of m times uy to the power of n. So here, because it's symmetric, they should have the same exponent. And fu are one-variable polynomials in this polynomial ring. And then in this case, we are hoping that we have small number of C4, color-isomorphic C4. Suppose we do not have many color-isomorphic C4, then that means, okay, if we don't have too many color-isomorphic C4, then that means ux plus uy should have we have lots of points ux1 plus uy1 equal to ux2 plus uy2, something like that. And that means we have, that means this image of the vertex set should have low additive energy or low multiplicative energy, depends on the structure of P or Q. So if P is like this, then it has low additive energy. If P is like that, we have low multiplicative energy. And low additive energy means that this set pi v have huge doubling. So basically, pi v plus pi v is of order n square, pi v square. So in particular, we have this image should have order pi v square, of order pi v square. And this gives us, because we also know that this image is linear, so pi v should be not quadratic, should be a square root of n. And then that also means the maximum degree of color class is at least a square root of n. So we cannot get a proper coloring in this construction. So actually, this gives us a lot of information on which polynomial we should choose. So firstly, we cannot choose a field of character 0. We have to choose a field of character p. And then also polynomial p should be expanding. And then I mean, you may be wondering if you choose an expanding polynomial, then this image p pi v will be large, will be quadratic on n. But the reason is, to fix this, we can choose k as a field of character p, and p is of order n. P is linear. So basically, this number of colors is cut off by this finite field p, by this character p. So basically, this phenomenon tells us we have to choose a polynomial p of character p, and p is linear. And also, okay, this is by notation because we have two p's. So this is capital P, means polynomial. Polynomial should be expanding polynomial in this ki. Okay, if you view this kxy as a field of character 0, then in that sense, P should be expanding. And on the other hand, we also want, we don't have too many color isomorphic C4s. So in that case, Px1, so this is a system of equations. We choose two arbitrary number A, B, C, D in K, and these represent the colors, right? We choose 4 colors. And so this system of equations, P x1, x2 equal to A, x2, x3 equal to B, x3, x4 equal to C, and x4, x1 equal to D, we don't want it have too many solutions, because each solution will give you a C4. And 2 solutions means we have a color isomorphic C4. And 3 solutions means we have 3 C4 which are pairwise color isomorphic. So in that case, we want P have small degree, have low degree, because large degree normally means high, more solutions. So we want P have low degree. Okay, so any guess, okay, any suggestion how to choose P? So P have low degree, and then the first non-trivial non-expanding polynomial have degree 2. So we can choose we can choose P to be a quadratic polynomial. And then P is expanding. So P cannot have the form like a sum of two one-variable polynomial or product of two one-variable polynomial. So it cannot be like, for example, it cannot be like x squared plus y squared. It cannot be like x plus y squared because it's essentially x plus y. So the polynomial we choose is easiest one in your mind is x squared plus xy plus y squared. But also in this case, the best we can do is we can prove F3 and C4. So back to the result we prove. So we can get 3. Because the polynomial we choose is quadratic, so it at least have 2 different solutions. So that is, we cannot have F2 and C4. So that is still open. So the question asked by Colin is still open. This one. Yeah, so, and then if you just use this polynomial and do some computation, you can see that, yeah, actually it works. And also you have to choose this correct P. So P should satisfy like something like equal to 1 more 3 and some other condition. And then by choosing this polynomial, basically you are good. Okay. And also there are some, I want to say some open problem. And this is my last page. So one of them is, of course, the question asked by Colin and Tompkin. So can we get F2C4 equal to linear, like F2C4? And currently, I think our method cannot give you anything about when k equal to 2. So maybe I think at least one more new idea is needed. And also, Colin and Tompkin proved F2C6 is actually not linear. It's n to the power of 4/3. And we know that FKC6 is linear for large k. Can we prove that F3C6 is linear? So there is an interesting phase transition for k equals 3. And if you still try our construction, this polynomial, the computation will be very difficult because here we have only 4 equations. So, and then you can see that, I mean, for any 2 of them, they share a variable. So you can cancel out some variable and to make computation easier. Not every 2 of them, so most of them, sorry. So because you have a matching, so it cannot be like, so like most of them, they share one variable, then you can just cancel some variable and simplify the computation. But for C6, the computation is much harder. And then, yeah, we don't know if we can get F3C6 equal to all of them. And also some other question about this previous result on non-expanding polynomials, including can we improve these 5/4 to 4/3? Because we already have 4/3 bound for Elekes-Ronyai and also for symmetric charter. So seems we are able to improve this bound. It is possible to improve this bound to 4/3. I mean, one may also ask if the bound is also true for 2 minus epsilon, just like some product conjecture. So actually, we think that should be also true, but that is a hopeless problem. So we just, I mean, a useless conjecture because it is hopeless. And also, can we generalize for other O minimal expansion of R, say like this exponential map? And this is, so basically our method, because we use O minimality, so our method should be available for this generalization O minimal expansion of R. But the problem for this case is we don't have a corresponding Elekes-Ronyai theorem. So currently, Elekes-Ronyai results for one polynomial Pxy, if PAB is small, then PA is either multiplicative or additive. So that result only work for polynomial. So if you have exponential function, then that is unknown. And actually, the proof of Elekes-Ronyai use algebraic geometry. So if you use, if you don't have algebraic structure, then you lose this irreducibility. So all the argument there just doesn't work. So we need to use some, I mean, if you want to prove this, we need to use O minimality, some nice topology in this O minimalities. But the original proof shouldn't work here. And also the proof given by Raz, Shari, and Shodimashi, it also shouldn't work because they basically use the algebraic geometry part, they just apply the argument by Elekes. Okay, so yeah, I will stop here.
Thank you, Yifan. Let's all thank Yifan for the wonderful talk. Are there any questions? Okay, I have some questions actually, if I may. So one thing is about this question about C6. From what you said, is my understanding correct that it is possible that even just the same or very similar construction to the one you had works? It's just hard to check?
It is possible, but it's hard to check.
Mm-hmm. Can you run some kind of computer algebra to do it for you?
We didn't try, but I think it's we didn't try actually, but I think it's pretty hard. I tried to compute it by hand, but it's just too complicated. Yeah, because as I said, you have to cancel out some of the variable. Otherwise, once you plug in some equation to the other equation, the degree will increase. So if you want to keep the degree to be 2, we have to like keep canceling out these different variables. And this doesn't work for C6. So this elementary algebraic trick doesn't work for C6 at least. Yeah. But I believe this construction give us like F, say 100 C6. I mean, if you just compute it. I mean, the degree increase, but it should have a bound like 100. Stop at 100. So if you can get a smaller bound here, but getting 3 is hard. Oh, I heard somebody say, oh.
No, I was saying that maybe that is true, and then there's some result in algebraic that would allow you to do that. There's something like Artin conjecture or something that might be helpful.
Okay,
no, but anyway,
I don't know that. Sorry.
No.
Are there any more questions? So do we in principle suspect that the F3 of any bipartite graph is linear potentially? Do you know any counterexamples to that? Is it too much?
Yeah, I think there's a counterexample. Actually, there's a result by Yangzer. He actually proved for general FKCL, C2L. So you have a bound for that. I think for larger C cycles, then you should increase this K.
I see.
I think K should be comparable with this cycle over 2, something like that. Yeah, length of cycle over 2.
I see. Okay, any more questions? Well, if there are no more questions, then let us thank the speaker again. And our speaker next week will be Eva Chabarka from University of South Carolina.